everybody. Today it's my pleasure to introduce you to Vincent Meunier. He's a professor, he's the head of the Department of Physics at the Rensselaer Polytechnic. And Meunier has earned his PhD in 1999 from the University of Namur in Belgium. He has been also a senior research and development staff member at Oak Ridge National Laboratory. But now, since 2010, he's at the Rensselaer Institute, Polytechnic Institute, where he is now a full professor. Professor Vincent has been having a very productive career. He's very widely respected by his contributions in the area of computational material physics, and has published more than 300 papers with an H factor of about 70. It depends on where you look, but at Google Scholar it says 70. And he also has had a long-standing collaboration with our department, mainly with Professor Antonio, but also with myself. We have a few papers together. And also a strong collaboration with Eduardo Girão at the Federal University of Piauí. He has come to Fortaleza a couple of times. Vincent, how many times have you come to Fortaleza? At least once, I remember.
I think 3 times at least.
3 times, all right. Yeah. A couple of times, and we are looking forward for him to come again. But meanwhile, while we don't have the luxury of traveling, it's actually a very great pleasure to have you here, giving us this very interesting talk. So please, Vincent, give us a little bit about what you have learned in the last few years about low-dimensional materials. Thank you very much for.
Thank you very much for the introduction, and thank you for all of you who are here today to listen to this talk. I'm going to give you an overview talk. So some of the things that you're going to hear, you've already learned in maybe your undergraduate classes, but maybe that's a good place to synthesize everything that we've learned and how we are moving ahead from there. So what I'm going to talk to you about today in this presentation is actually 3 revolutions. I'm going to talk about the first revolution, the first quantum revolution, the second quantum revolution, and I'm going to talk about the nanoscience revolution. It's a lot of revolutions. So we are going to discuss, this one. So you will see a little bit that sometimes in science, we use words a little bit out of context, like revolution. I mean, this is pretty serious when we talk about revolution. But you will see that there's been, in terms of as scientists and engineers and so on and so forth, information technologists, there's been indeed a lot of revolutions. So I'm going to try to give you a little bit of an overview, looking at those 3 revolutions, how they are intertwined, and how how the first one, for example, enabled the second one, and how the second one enabled the third one. And we are right now still in the second quantum revolution and the nanoscience revolution as well. So I'm going to give you a few examples and try to give you a little bit of an idea how we can go through this process here, intellectual process. So the first revolution I want to talk to you about is the first quantum revolution. And as you know, this is a revolution that started at the early 20th century or late 19th century. It was the time where everybody believed that we knew everything about everything. So I don't know if you've noticed this in life. Maybe when somebody comes to you and says, "Oh, I understood everything now," this is usually the time when you say, "Okay, probably it's not true." And of course, it's very easy to say that after the fact. It was like 120 years ago, but still, as a rule, as a very good rule in science, don't listen to people who tell you that everything is understood, because that's usually a recipe for disaster, as we say. So just to give you an idea, just to give you a quote, because we see quote a lot, but this one is the quote from Michelson, which is of course a very well-known person in the history of understanding electrons. Of course, there are quotes everywhere, but one that's interesting to look, and I highlighted it here in yellow, it says that, so back in 1894, seems that probably most of the grand underlying principles have been firmly established. So that was at the time when everything was understood, because people could understand Maxwell's equation. They couldn't, electromagnetic theory. They could understand theoretical mechanics, that kind of thing, and also thermodynamics, as you know. I mean, classical thermodynamics, I should call it. And that was in the time 1894, and everybody believed that's it. We know everything by now. So there is no future for jobs like physicist or chemist or things like that, because everything is understood. Well, you certainly know now that if you are in the room where you are listening to this, probably at home, or I don't know exactly how you're working this out during confinement, but you know that if you are currently a scientist or a student, this is not true. We are not everything is known. Actually, there's still plenty to understand. And so one of the first experiments that showed that this was indeed the case, that clearly in 1894 the science could not explain a lot of experimental findings, is related to this experiment. Of course, this experiment from 1801, which is of course the young, the double slit, the young experiment. This is an experiment done with light. This is not a quantum mechanical effect. Of course, this is an interference of light going through two aperture here, shown as S1 and S2, and the interference of the waves basically led to the measurement on the right hand side, and those fringes basically give you information on the wavelength of light. And so even there, the history behind understanding light is a long one, but the point here is that we could understand that the wave nature of light, a monochromatic light, was responsible for this interference pattern. So that's something that had nothing to do with quantum mechanics. Really, it was in 1801. Now, what happened is that while everybody believed and understood everything about material, there was this experiment from Davison and Germer in 1927, where they tried to repeat this experiment, but in this case using an electron gun instead of light, instead of I would say a laser. Of course, a laser was not used in 1801. It came well later, but anyway, instead of a monochromatic source of light. And so in this case, the idea was to have electrons and to throw the electrons with a gun, I mean, shoot with a gun, basically, this double slit experiment, the same way that was the Young's experiment took place. And so what those experimentalists notice is that if you look at the plate if you put a plate behind the screen here, you start to see impacts of electrons. And in fact, if you, at the beginning of the experiment where you have a low flow of electrons, you see basically that you have random, what looks like random distribution of impact. So the impacts are the bright spot on the screen. And if you keep going and you increase the recording time, you see more of those. Still nothing really clear happens, but if you keep going, well, maybe if you have a good eye, you start to see that there is some kind of fringes. It looks like there are areas that electrons rarely touch. I mean, I don't know if you see them with my pointer here, but we are going to see them better here in D. In fact, even more when we have more impact, we start to see those fringes. Remember, this is an old experiment. It's an experiment about a century ago, so this was very nice. And so what happens is that it looks like the electron behave exactly the same way as light behaved in the Young's experiment. And of course, you know by now, it's because this was an experiment that basically demonstrated that electrons are not just particles in the classical sense of the word, but also waves. They behave like waves, and this was work that led to the de Broglie work in 1929, who actually basically provided a formal relationship between the energy of the electron and its wavelength. So that's already showing that, yes, something is happening with material at that scale. Of course, there were other examples, and like the experiment in 1887 by Hertz, the same Hertz that with the units for frequency comes about, where the photoelectric effect shown that what matters to extract electron from a material is not the intensity of the light that you shine. Instead it's the energy of the light that you shine. So the frequency matters more than the intensity. So it's not the number of impact you have that matters, but it's actually the energy of the impact. And so what it showed is that basically that the photoelectric effect demonstrated that electrons, again, those electrons that we start to not understand anymore, occupy very clear quantum state that cannot occupy a continuum of energy state. They are quite quantized. So that was one of the first demonstration with the photoelectric effect that that shows that the energy is quantized for the electron that live in a material. And of course, as you know, one person who studied this a lot was Albert Einstein, who in fact explaining that photoelectric effect was one of the reasons he got the Nobel Prize in physics, and the relationship between energy and frequency. So another example of what happened there that explain again that we did not understand everything back in the late 19th century, early 20th century, is the hydrogen atom and the fact that only a certain number of energies are possible for the electrons. I show this example because all the students who are listening today who took an introductory quantum course, of course, know about this because you solved the hydrogen atom. So you solved for the energy level of the hydrogen atom, and those levels are purely quantum mechanical. They could be explained by the Bohr's model, which needed to be refined later. But again, the Bohr model came from the quantization of the momentum and quantization of energy. So again, something is missing here. And of course, maybe the favorite experiment that shows that things are really different at the quantum mechanical level is the Stirner and Gerlach experiment, where you have electrons. Actually, here it's one electron. These were atoms, like I think it was silver atoms. So basically, with a s electron that actually dictates the physics of this. And so what happens is that if you basically think about a spin 1/2, an electron basically, okay, just to simplify, is actually thrown between two. Within a magnet like this, which is non-uniform. I'm not going to go into details, but it has to be non-uniform to allow for deflection. The point is that if you have a classical moment, a magnetic moment, you know that the deflection is going to be proportional to the projection of that momentum, which is a vector, on the magnetic field. So in other words, you know that there will be a maximum deflection because, well, the momentum has a certain value, but in principle it should be continuous between a maximum and a minimum deflection. That's what classical physics would tell you. Well, the Stern-Gerlach experiment in 1922 showed that it's not the case. What happened actually, and this is the plate from 1922, is that you only have two deflections. You have only two traces shown by the yellow line, which are either up or down. And so that means that, again, there is a magnetic moment associated with the electron, which is quantized. Again, a big deal, a big finding. And now, one thing I'm going to do from now on is to describe those states which are weird, that quantum mechanical state. I'm going to describe them as a up and down, and I will use a Dirac notation, which is the brackets, and this cat notation. In fact, this is a cat. When I teach this in quantum mechanics, I like to tell students that it's actually very convenient to use a different notation, because that way you do not need, your understanding does not have to be affected by your understanding of math or classical physics. You're basically entering a different realm. So we are going to use this notation of the cats in the moment that come. So we see that this means that basically the projection has only two values. So let's try to look a little bit more into this. What's the weirdness about quantum mechanics when we get to this? So for that, let's forget about electrons, because they are way too complicated and we don't necessarily understand them. But instead, we are going to consider that we have monsters, okay? And we only have two properties for monsters. One of them is happiness, or I would say emotion, the emotion of the monster, which can be either happy, so you see the two bottom one are happy, or sad, that's the top one. And then there is another property of those monsters, which is the color. So they can be either green on the left or red on the right. So very simple problem, right? You have monsters who can be happy or sad, or green or red. There is no correlation maybe between them. We don't look into that. There's this. And then we decide to create a large population of monsters. So a very large population with basically the probability of finding any of the property is constant. Okay, it's the same, it's uniform. So we have this big bag here. Of course, it's a bag from a theorist. You see, you have all those sort of monsters, and you can count them. There are as many green as red. There are as many happy as sad. One thing that's very important, and this is the warning I have on this slide, we can only measure one characteristic at a time. So we cannot measure than one. This is just the fact. We cannot tell two things at the same time. And in fact, you will see in science very often two properties, or even in real life, getting two properties at the same time is essentially impossible. You have to make two measurements. Think about that a little bit. I think it's an interesting point to think about. Anyways, so we can make a measurement and decide if we have a green monster, a red monster, a happy monster, a sad monster, okay? There is another thing I have to tell you. It's what we call in physics a two-state problem. So the monster is either green or red. The monster is either happy or sad, okay? So when we make a measurement, okay, that's not an additional emotion to emotion. There is no blue monster in my experiment. That's what I'm trying to say, okay? Good. So let's try to see, and we are going to use a Schrodinger experiment, the one I explained to you that shows the spin up or spin down. But instead of having my Schrodinger experiment that measures the spin, I'm going to do a Schrodinger experiment that measures the color of the monster. I mean, I can do this. I'm a theorist, so I can certainly do this. This is my box with full of monsters of all the time, and I measure this. On the top, I'm going to get green monster. On the bottom, I'm going to get red monster. And I'm going to call that experiment the Q color. So basically measures the quantum color of my object. I say quantum because maybe something weird is going to happen. So I'm keeping the door open for the weirdness to happen later. Okay. So this is my experiment. All right. And what I'm going to do, I'm going to decide to cut off all the monsters that are measured red. I just don't consider them anymore. Okay. Instead, those green monsters that I've selected by measuring the color, right? I only keep those at green. I decide to measure again the color, just in case. Well, it turns out that if I do this, so just like to explain to you what I'm doing here, this experiment there, which I call SGZ, okay, Schrodinger measures the color of the monster. We are going to keep all the green monsters, and we are going to again measure the color. So the question you can ask yourself is which color is going to come out of this? Okay, I cannot check the result, what you're saying in the chat here, but you can try to answer this question. How many of them are going to be green? How many of them are going to be red? Well, frankly, if anybody of you says that some of them will be red, I need an explanation. Of course, all of them will be green. If I measure the color of green monsters, I find green. Not really quantum mechanical so far, is it? That's what I have. Okay, so let's try to do another experiment. Now we are going to also consider another apparatus, which is called Schrodinger-X, and it's this case, it measures the emotion. I'm going to call it Q emotion, so it's a quantum emotion, so that way I keep the weirdness. And again, same experiment as before. I'm going to only select the green monsters. Okay, so that's what I'm doing. And then I put my box, SGX, which is going to measure sadness versus happiness. So I'm doing this. All the monsters that I measured on the top will be happy. All the monsters on the bottom will be sad, like this. I put it in blue because I could not measure the color. So since I do not know what it is, I'm just going to use I just know that happy or sad here. Okay. So very good. So this is what I do. So just so it's clear, I'm just measuring quantum properties right now, just on a piece of paper. All right. Okay. Now ready for experiment 3. Same thing. I measure the color, only keep the green. Okay. Now I measure the emotion, only keep only going to keep the happy monsters. So you get this. I look at all the monsters, keep the green, and then I only keep the happy monsters. So now the big question is, let's check the color of the monster again. So I want to check the color of the monster. So the question I'm asking you is, what do you think happens? How many of them are green? How many of them are red? I can't check the answer you're giving in the chat or whatever. If we were in the room, I would actually ask a show of hands, but it's fine. You should know the answer, right? If you took quantum mechanics, you know that, in fact, if you do this experiment, you'll see that 50% of the happy monsters are now green and 50% are red, all right? So what happens quantum mechanically is that you cannot know both the color and the emotion of the monster at the same time. Because if you determine that a monster is happy, that you no longer know which color it is. And this is the same way if you measure the color, you do not know the emotion. So this is this idea of properties that are not compatible. Well, for those who do linear algebra, you know that simply means that those properties correspond to eigenvectors that are not eigenvector of the same operator. So of different operators. So that's the issue we have, and this is basically quantum mechanics. So quantum mechanics is basically related to this experiment of the monsters and the Schrodinger. And so what we can do is to go back to our notation of bra and cat, and those cats are basically the fancy way to represent a quantum state. And we are going to have 4 of them. We have sometimes a happy monster, an unhappy monster, and a green monster or a red monster. And I know that I can have all this outcome. And in physics, or in algebra, we call them basis vector. And so what happens, of course, is that what the reality of the experiment I just explained to you, and this has actually been done experimentally with electrons, and the 2 properties were spin along Z or spin along X. The reality from those experiments is that, so S will be sad and H will be happy, G green and R is red, is that the thought experiment I just showed you is that the sad monster is a linear superposition of a green and red monster with some terms alpha prime and beta prime that have to be described. And so the probability of finding a sad monster being green or happy monster being green will be alpha square or beta square. So this is basically quantum mechanics in a nutshell. So this is related, obviously, to the uncertainty principle that we know, or that we have heard, we hear a lot in the popular media, is that we cannot know the emotional state and the color of the monster at the same time with certainty. Of course, usually we don't talk about monsters because this is kind of for pedagogical reason. However, another example that you hear a lot is the cat, is the famous Schrodinger cat that's both dead and alive. And you can show that using also those cat representations, the quantum representation, where the state of the cat is equally likely to be alive and dead. And you cannot tell until you make a measurement. Okay. And in fact, the problem with this is that you cannot resurrect the cat. If you measure the cat to be dead, you basically collapse your wave function and you basically impose the result. Okay. So I know I spent quite a bit of time on this, but it's because I think it's fun. So the first quantum revolution was actually to explain all this. So there were a lot of very smart people who worked on this, including Schrodinger, Pauli, and Dirac, and others. And the revolution was to be able to explain all those phenomena. And in particular, if you look at Schrodinger equation, which here I provide on the top here using the notations I just introduced, the Schrodinger equation can be solved for any system in particular, in general. But it's not easy to solve this problem mathematically, but the point is that if you were able to solve this, you would actually know all the quantum mechanical properties of an object like this. So you know all the properties are written in this state, which we call the eigenstate of the system. This is, of course, a very complex mathematical object, and its modulus provide the probabilities. So that's nice. That's what the first quantum revolution was about. And I spent about 20 minutes on this now, but I'm going to show you where this brings us. So this is time to move to the second quantum revolution. So all those equations came from the 1920s, 1930s. There were a number of Nobel Prize that were awarded. There's been a lot of work going on. And in fact, many people are doing quantum mechanical studies, both theoretical and experimental, in fact, and it was all enabled by that revolution. So it's really changed everything. I mean, when we talk about transistor today, the transistors is really based on semiconductor, whose properties can only be explained by quantum mechanics. So pretty much everything is based off quantum mechanical manifestation in the real life. Now, of course, as you know, in the history of humankind, the first thing we try to do, the first thing is that we end up with a situation we do not understand. Just like think about this Schrodinger experiment. Then we develop a theory to explain it. And then we try to explain more and more and to see how we can expand it. Then we modify it to make it work. And then after that, we say, well, maybe I can exploit things. I can do alchemy, basically. I can create new state of matter based off the understanding I have of quantum mechanics. And it is exactly what happened with the second quantum revolution. And in fact, the second quantum revolution started maybe 10, 15 years ago, and it's actually in full force right now, which is really to try to exploit quantum properties, but from basically creating new systems that are not natural systems, but which have interesting quantum properties. And an example is quantum computing, and of course, all the associated effects. And for that, I'm just going to show you an example again. Remember the computer bit. By the way, computer bit is still what we are using right now in computers. There is no quantum bit yet. So if you want to buy a quantum computer, do not spend good money right now yet, because it's either too expensive or there is no such a thing. Okay. So anyways, the word quantum is used too much in the everyday's life, but this is why you have talks like this, is so that we know what we're talking about. In any case, a computer byte is 8 bits, right? And we know a byte, a bit can either have a classical bit can either have a 0 or 1. There is no other possibilities. So it's either a 0 or it's a 1. And we can, in fact, encode a lot of information like this, right? So we have 2 times 2 times 2, so basically 2 to the power n possible words that we can use with n bit. Okay, so very good. So the manipulation and operation of those were actually enabled by the transistor that was developed in 1948 in Bell Labs. And there, it was basically applying semiconductor properties and diode and that kind of thing, and transistors. And you can actually address those properties, and this is nice. Now, this is classical, kind of, right? It's definitely classical. But I say kind of because, of course, the transistor uses quantum mechanical properties. But the point is that, we can also do what's called a qubit. And so a qubit is the basic unit of quantum information. So it's no longer that we have a bit that's either 0 or 1, but it's a superposition. Just the same way as a monster is not either green or red. It's a superposition of those two properties. Yes, it's true. When I measure it, I collapse the state. But before I measure it, it's a linear combination. So just the same way as we have monsters that can be red and green at the same time, so to speak, the state of a bit, of a qubit, can be a superposition of a 0 and a 1. So why is that important? Well, let's just see a second before how we do this, just to introduce you to an important concept, which is called the Bloch sphere. So the Bloch sphere, it basically allows you to see the proportion of 0, which is on the top of the z-axis, and 1, which is on the bottom of the z-axis, the negative values. And so the state vector, the cat state vector, is actually a combination of, you can use 2 angles on the sphere to describe where the state is, which is basically, so that in that way, the state is a superposition of 0 and 1. So just so you understand why we work on a sphere, is because all the points on a sphere will have the same length for the vector, right? And of course, the length of the vector, the square of the length, is a total probability, which of course we want it to be 1. Why? Because we want to have the certainty that the state exists, basically. Okay, so this is the idea that why we talk about a sphere. And so you have two properties, the 2 angle, phi and theta, that you can use to see where the state is located on the sphere. And so that's nice because you have, instead of having just a 0 or 1, you have a very large number of information that you can store in a qubit. And in fact, instead of having n bits, for example, you have in an n component qubit, you have n to the power n minus 1 complex numbers. So you have really a lot of information that you can work with. So this is really the second quantum revolution. This is the basic of it. This is the idea that we are exploiting the possibilities of storing much more information that we can in a regular bit. And so the same way as when we have a word or a byte in classical numerical property, classical information theory, we need also to be able to modify and read out and write and so on and so forth those properties, those qubits. And so what we do, and this is really very much in the realm of physics, and is the idea is that we end up with a state, right? A state psi, which is a superposition of 0 and 1, which can be manipulated by operators. Just like we work with operators in physics in general, we can also use an operator. And there are different operators that can modify the state. And for example, well, there are a number of them. I'm just showing them here. The Pauli X gate, which is a NOT gate, you can see the effect of the NOT gate on 0 and 1. So for example, if you have a state that's in 0, that means that it's the operation of the Pauli X gate will be to transform it into 1. And if you have a state that's in 1, it's going to be transformed into 0. You can see that very easily. So basically, it negates the state. If it negates the state, it's called a NOT gate. So this is a kind of the basic gate that you can use. And of course, for those who have had quantum mechanics before, I hope you recognize this gate. This is actually one of the Pauli matrix. That's so you know there are 4 Pauli matrices, and this one is one of them. And it turns out that the application of the Pauli matrix on this system is actually a NOT gate. There are other quantum logic gate, like for example the square root of a NOT gate, which can be obtained by manipulating the different operators that we can operate. And again, these things now can be modeled, and there are even some libraries that are available in Python, for example, for you to model this kind of thing. So you can actually play with the different gates just the same way as we played with electronic component on the board when we were children and trying to learn some electronics. So this is not a dream. This is actually reality. I mean, there are physical realization of all those qubits. For example, using the spin system, the nuclear spin system, the quantum dots, and so on and so forth. And you can see in those few examples that this is the realm of physics and material science as well. So there's really a lot of promises for quantum information and quantum materials as we move forward. And as you know, there are also quantum computers. This one is an example from IBM. Is actually an example from about 6 months ago. So they are probably updated one at this point. But people start to be able to put those different gates together in a computer and to be able to manipulate the different states, the qubits. So the question you may ask yourself is that if it's so cool, if it's so nice, why don't we see more of them? Why is there so few quantum computers? Or why don't I have to worry about when you wake up in the morning if you have a cat, if you're lucky enough to have a cat? Why don't you have to worry about if the cat is going to be dead or alive when you find the cat in the kitchen? Well, because it turns out that in real life, the quantum mechanical effect can in fact be washed out by decoherence. And the decoherence is, in a nutshell, is the fact that the states are being, so for example, the cat are being projected on one of the states by the coherence, basically, by the fact that you have decoherence at normal temperature. So most of the quantum state can only be seen at very low temperature when you don't have the issue with decoherence. And I'm going to go back to that in a second. I always find this funny when I look on a bookstore. This is just an example of all the quantum. So here are all papers. So these are novels all about quantum. So quantum physics for hippies, for example, Quantum Mind, Quantum Doctor, And the quantum doctor here is not the professor who teaches quantum physics. That's not him. Even dish soap for the dishwasher, like Finnish quantum, and so on and so forth. So all those words, of course, are completely used incorrectly. So we see quantum much less than we actually see novels with the word quantum in them, at least at room temperature. But let's go back seriously more here. The problem with coherence, the issue of decoherence means that you are basically losing the quantum mechanical aspect of your state. You essentially project your state in one of those bases that I was mentioning before. So the reason for this is because the system, in order to solve this equation that looks pretty innocuous in yellow here, it turns out that for the state to remain a stationary state, it has to be an eigenstate of the Hamiltonian, right? And in reality is that the existence of the rest of the world or in the environment and any interaction with the environment is going to break the coherence, because if you're more mathematically inclined, is basically saying that the Hamiltonian is no longer the Hamiltonian H, but it's actually modified by a Hamiltonian, a perturbing Hamiltonian, which comes from the environment. And so because of this, the state that you want to work with, like the cat, okay, like is it dead or alive, like the Schrodinger cat, the state in that case is no longer an eigenstate, therefore stationary state, and it's short-lived. You can no longer use that state to describe your system. So that's how you can explain this. Okay. So now it's time for me to move to the third topic, to the third revolution. So the first revolution was to say quantum mechanics is a thing that's needed to explain experiment. Second quantum revolution was to say we can exploit this to get something completely new that is artificial but very promising. Okay, and then now it leads me to the third revolution, which is the nanoscience revolution. And of course, you know very well what I'm talking about, since the university I'm giving this talk for has been leading in this area in many different topics. So the point is that nanoscience revolution, how does that help quantum revolution? Well, as I told you, there is the issue of coherence, of being able to get material that we can explain atom by atom, basically, and there is no uncertainty on explaining on the material we're working with, so that we can predict exactly what quantum state we can have, and we don't have fluctuation that would actually remove basically the coherence that we are seeking to do quantum physics. So basically, nanoscience provides a support for quantum. Basically, it provides this place, this material that will have quantum state that we can use for quantum applications. Okay, so the quantum revolution came much later than the nanoscience revolution came much later than quantum revolution. Of course, there was this famous quote from Feynman in 1959, even though this is probably a stretch to say that Feynman invented nanoscience. That's not quite the case. The word nanotechnology was introduced in 1974. And then there were work in nanotechnology from Eric Drexler. And in my opinion, one of the key finding, the key development in the world of nanoscience was scanning probe microscope, scanning tunneling microscope, and atomic force microscope, which were basically developed in 1981 by researchers at IBM, and actually got the Nobel Prize in 1986. Why is that so important? It was very important because not only those tools, STM and AFM, allowed to observe atoms, to see where they were. They also allowed to modify structure by moving atom around. So this is really the nanoscience, basically understanding what's happened in the low scale. Nanotechnology is when you start to manipulate. So both STM and AFM allowed both of those things to happen. And of course, after that, it was purely the human imagination to move forward and create new structures and new interesting things. So the birth of nanoscience, one of the things, and I'm a bit biased, obviously, because I've worked a lot in carbon, was the work done in carbon. And the reason why carbon had such a huge impact in nanoscience is because first of all, carbon is very abundant. It's not very expensive. Second, you can create a lot of allotrope, lots of different structures just with carbon, so that simplifies the growth process a lot, since you only have to worry about one ingredient essentially, just to simplify. And then the beginning of all this was related to a lot of development in chemistry, where there was the understanding of C60, the soccer, the football ball, right? So that was from Kroto, Smalley, and Curl, and it got Nobel Prize in chemistry in 1996. There was a lot of work going on in fluorines as they were called, and there's still a lot of work. The huge thing about, but it was still a little bit like in chemistry, really. You have a close structure, so it's like a molecule, really. But the huge development was made in 1991 with the first reported measurement of carbon nanotube, and it was done by Yejima, who's pictured here. And that was since the 1991, 1995, there's been a lot of work initially on carbon nanotubes. And in fact, many experimental techniques have been developed just to try to understand it, which was, of course, very important, because then people developed techniques and know-how to work at that scale and then apply to many, many other structures. And this is what happened in 2004 when people started to work on 2D layer of graphene, which was actually also led to a Nobel Prize in 2010 by Geim and Novoselov and many other researchers working in the field as well at those early days. The importance was not just to be able to create a two-dimensional structure of a perfectly positioned atom, but also to understand new physics that came from the low dimensionality of those structures. So when you work on those structures, as I'm personally a computational physicist, and I do a lot of work in different materials like this, we're always interested in understanding the quantum mechanical properties of them. And so we solve Schrodinger Equation. As I already showed you one version of it, this is essentially a rewritten version of it, but I'm not going to bore you too much with equations here. The point is that we can solve these equations now numerically, thanks to a lot of development in the theory of quantum mechanics. For example, the work from the density functional theory, which was developed by Walter Kohn in the 1990s, and he also got a Nobel Prize in chemistry for this development, along with people who developed quantum chemistry work. Anyways, the point is that we can now understand material more and more closely by solving that equation on actual material. And in fact, I've been doing a lot of work in that area myself, as shown in some example here. And I'm just going to show you a case study on carbon materials from my work, just quickly to show you a little bit where we are going with quantum materials and how we can enable the second quantum revolution. So an example here is that if you take a piece of graphene, as I said, so a 2D layer of material, and you cut it in nanoribbons, you are essentially imposing the wave function, so the electron, the quantum mechanical property of the electron, to be confined in a certain object. So if you remember the very early, one of the first application of quantum mechanics that students do is to have is the one-dimensional well. Well, think about this. It's like a well as well. So you basically impose the electrons to be inside a small ribbon. And when I say small ribbon, it's about 3-4 nanometers across, which is small. So you can do this and play basically with electrons and imposing different quantum mechanical constraints to the wave function. So when you look at graphene, of course, they've been it's well known, and graphene is very interesting with this Dirac cone here. But it's a metal. It's a semi-metal. But the point is that if you look at the Fermi energy right here with the horizontal line, the conduction band and valence band touch at one point, and in fact there is no gap. So the gap is zero. Okay, so that means that it's a metal. Now, if you try to do electronics, you usually don't want to have a metal. You prefer to have a semiconductor, therefore, so that you can excite electron and you can also gate it. So, of course, we always use semiconductor when we try to do diode transistors, right? So graphene is not a good idea, but you can actually manipulate this by confinement. As I said, you can confine the electron within a certain space. So, for example, if you take graphene by cutting it off, so you basically impose the electron to only be stuck in a certain width of the graphene sheet. And all that is related to the Heisenberg principle, which is a consequence of quantum mechanics, that says that the size of the object is the size of the physical object will impact the properties of the electron that's placed in it, basically. So the profound effect, of course, is on the state, on the energy you need to actually move electrons from a state to another one, just like the photoelectric effect I explained at the beginning of this talk. So let's talk about graphene nanoribbons, and they can be made in different size and different width. And in fact, experimentally, it'd be great if were able to do all this, because theory, for example, the theory here from Stephen Lewis' group predicted that the band gap, so the energy you need to excite electron, depends on the width, on the number of carbon you have across the width of those systems. And of course, this is nice because this is kind of quantum materials engineering. Just by changing the number of atoms you have in the width, you can basically manipulate the wave function. That's basically what it's doing. Now, the problem is that if you do that, you need to have something extremely clean. Otherwise, you have the decoherence I mentioned before. So you cannot really manipulate or predict. So what would be great to do is that if we can just do like we did when we were kids and play with Lego blocks. So if we had some Lego blocks and put them on a surface and create something that we want, highly ordered, that'd be great. Because then that we could predict what's happening. Well, it turns out that these people that I'm listing here in the references did not, I mean, they may have played with Lego, but I don't know about that. Those people actually are chemists and physicists who, in fact, developed techniques to do just that. And of course, the first work was in 1901 from Ulman and Bilecki, so probably didn't work with Lego block at that time. But the point is, you can, if you have those Lego block like these hexagonal rings, and then you can place them the way you want, you're going to create different types of those containers that I mentioned before, like, for example, the 9AGNR. So this is just a name. I'm not going to spend too much time. It's just 9 dimer along the width. But this is nice to do on the screen. It turns out that it's also possible to do that in reality. And this is done. This is done actually called the Ulman Coupling. It can be done from certain precursors. So physicists, and this work was actually done by Klaus Mühlen and Roman Fasel in 2010, were able to assemble those Lego blocks, if you will, to create those perfect ribbon of graphene together. So that works really well, and the US basically created a perfect quantum container here of a certain width, seven atom. Other things can be done, like this work. This was a work I work with people in France. There, instead of having the ribbons, if you will, the narrowest possible armchair, but you can also do this and explain like the experimental result. You can explain it very well with the calculation on the top, and you can explain the result on the bottom from there. So there are many things that can be done. For example, you can also use another building block, another Lego block, and you can put it together and doing some chemistry here, again, the Ulman Coupling chemistry, and create this particular structure here. And again, this is not just a figment of the imagination. You can see the experiment both in STM or in non-contact AFM, right on the right-hand side, and you can actually see that each atom is exactly where you want them to be. I mean, this is a big deal. That's not just a video game. You can actually create structures where you know exactly where each atom is located. And when you have that, you can predict the wave function. And if you can predict the wave function, you can really understand the fundamental properties of those materials. So that's what's exciting about that. So remember that I showed you the plot of the band gap. In fact, this plot here, and he may be in attendance, is actually coming directly from from the thesis of Edu Costa-Girard, who got a PhD from Sierra a few years ago. I'm not going to say how many years ago, otherwise he may feel older. But I actually used that from his thesis from a number of years ago. And the point is that the two structures I mentioned, it was a reproduction, of course, of the work done by Stephen Louis, but using his method. And here you see that the two examples I showed you with 7A GNR and 9A GNR, they fit exactly on the band gap I have here. Now that's nice, but the question is experimentally is that can we actually also
Oi.
Estamos tendo um problema técnico, o professor Vincent deve ter tido um problema na internet dele, mas a gente já deve estar voltando.
Ok. Vou aguardar então um pouco até o Vincent voltar. Só espera um pouquinho, pessoal.
Okay, so
Hey, Vincent.
Okay, so something you can't believe is that
Vincent, I think he has to put you back.
Okay.
Because I think you fell off, right? Can you share your screen again?
Oh yeah, I'm in the show right now. That's what they say, right? Can you hear me?
Yeah, we can hear you, but your presentation is not up.
Oh yeah, okay. Let me try to do that. I'm very sorry about this. I'll explain to you what happened. Okay, so all right, these things happen. This is what happens when we're online.
Yes. All right. You're all set now.
Yeah. Okay. So you know what happened? I've lived in this place for 10 years. It's the first time we have a power outage because of thunderstorm. So it had to happen now. So maybe something is happening. Anyway, let me try to go back where I was. So we were talking about those band gap that we can engineer, basically, and basically play with quantum mechanics. So the question you can ask is, can we go to other places on those curves? And the question is, because we want to change the band gap, basically. And the question is, you can. And this is where we use everyday's intuition from scientists, is say, if we have two of those ribbons, can we fuse them to make a bigger one? And if we make a bigger one, we can move on the curve I just showed you. So basically, you want to do this. And you can do this zipper, and you can actually do that, create two ribbons, put them together with chemistry, and create a larger one. And so if you want to write, you have 2 9 GNR, and you create 18. Remember, the 9 is the number of dimer you have along the width. Okay? So you can do that. You can do that with 7 as well and fuse them. In fact, this is work that was done at Oak Ridge National Lab with my collaborators. And this is the kind of experiment that you can find with a non-contact AFM. So you see that you have created a perfect quantum object again. So you are basically engineering those quantum containers where you impose the electron to have very established constraint on the side. So this is another example here where you can put 3 of them. You can zip 3 of them and create a 21. And then you can do that with other GNR. But the point remains that you can start to play. You can create all those quantum containers, and I like to insist on each one of them, we know exactly where each atom is located. So that means that we can really make predictions that are as accurate as it gets. There is no uncertainty on the prediction, since your equation, Schrodinger equation, which is deterministic, is uniquely defined, since you know exactly where each atom is, and therefore how the potential looks like. Now that's all nice, that's great, you can do engineering like this, band gap engineering, but you can also, it turns out that the zipping effect does not always work that way. In fact, if you ever try to zip I don't know, in Brazil you have to worry so much about cold weather, but sometime in the north where I live, in the winter we have to put this kind of coat. And if you are in a hurry, sometimes what happens is that the zipper does not align very well. And so, well, that means that if you do that, the ribbon is not quite nice. It looks more like something like this, okay? So what happens is that you start to have a situation where you have a piece that's zipped and a piece that's not zipped. So you say, well, it's too bad because it's not what I want, but it's actually what happened experimentally. You can see some of those there. And so that's where you say that you failed to do what you wanted to do, but it appears that you created something even more interesting. And what you've created that's even more interesting is that now you have created a heterojunction. Remember, I told you the band gap depends on the width. Now we have a perfect width on the left-hand side, followed by a larger width and then a smaller width. So basically you have created a series of band gap. So basically you have changed, you start to engineer this quantum potential that's not uniform in space. So that's really nice. So you end up with something like this, which is essentially a quantum dot, since the electron that are stuck in those 2 regions here. So I hope you see my pointer. They actually cannot escape, so they behave like if they were in a quantum dot. So that's what happened experimentally. And again, you know exactly where all the atoms are. In fact, I like to show this result from a couple of years ago, because it really shows that the knowledge of the position of each atom is so important to understand what's happening. And in fact, on the left, it's an experiment. On the right, it's our theory. And then you see that if you look at the different states, the symmetry and the properties are exactly as predicted. So you can actually, this is almost embarrassingly close. It's very close to what we have experimentally, simply because we really have a handle and control over how the electrons are behaving in the structure, which is exactly what we want to do in quantum material. So one thing that you can also do quantum robustness, as we call, and this is the field now of topological material, where the properties are basically protected by the fact that they have a given topology, right? So this is something that's very important. I'm not going to talk too much about this because we lost a few minutes because of the power outage. So I'm going to skip directly to another aspect of the work, which is graphene with a twist, and I will end like this so that we do not go too much over the time. Graphene with a twist, as you know, if you take graphene, it's nice like this. Looks so let me just do this. If you have graphene, it looks like this, but graphene usually comes in multi-layers, and in fact, there is no reason why you could not twist the layers compared to the other. So this is what happens. You have a blue crystal over the brown crystal. And when you look at this picture, you see, maybe you see that if there is not too much lag in the video, you see that they are super periodic cell. For example, in this case, you see that there is a superstructure. So basically a structure that has a larger lattice constant that's coming from twisting one layer compared to the other. And this has been a very big deal over the past few years, because people found that for a very specific angle of the rotation, you have completely new physics happening. So you have completely quantum mechanical effect happening, related to superconductivity, related to all sorts of things that happen exactly at a magic angle. We call it magic angle because there's a specific angle where the electronic properties are exactly right. Okay, so imagine that you have those two layers, and you say you don't have much interesting properties, but if you have the right angle, it's like turning on this specific physics that's so exciting. So that's very nice, because that you have a total control on the quantum mechanical properties. So what I've done in my group is try to understand the phonons, so how the vibrations are affected by the twist angle. And this is an example of such a system that we looked at. And without going too much into the detail, what we were interested in is to understand how the band structure of the phonon band structure of that system, which of course has many bands, because there are many atoms, how does it compare to the phonons of the graphene, which is only, bilayer graphene, which is only 4 atoms per cell. So that was a big deal to do this, and it's when my student Michael Lamparski worked on his thesis that he just defended, is to try to find a way to unfold the bands into the Brillouin zone of the AB stacked bilayer graphene with only 4 atoms per cell. So I'm going to show you an example of that in a second, but what really matters here is that when you look at the displacement field in a bilayer graphene, you get this very complicated graph, this fairly complicated graph, and what you see in that kind of things is that you start to develop a region of AB stacking, of AA stacking, and in between you have something that looks like actually a soliton network. So it's like a grain boundary, and that grain boundary basically defines the properties of your material, and this is what makes it so interesting. And in fact, those properties can be seen in the unfolded band structure I mentioned to you. So this is a bit of a complicated graph too, but for people who are familiar with the band structure of bilayer graphene, you see that when you have a twist, there is a splitting of many states, and those splitting of those states is actually is a signature of the magic of the angle that you are using, that you are rotating your structure by. And so what happens is that new physics is actually taking place, and in this case, the physics is not so much in the electrons, but it's actually in the phonons and how the quantum of vibration behave in such a quantum material again. So in particular, one thing that's also always interesting, and I show the students, is what's happening here in those low frequency region. And those low frequency region is actually related to two specific modes, which is the 2 layers breathing. So it's a breathing-like mode. Another one is the shear mode, when the 2 layers are moving like this. So these are 2 properties that can also be used to understanding the angle. And in fact, we can follow those different frequencies as a function of twist angle. And without going into too much detail here, you can actually find a one-to-one correspondence again between the structure, which is complex, and also all the vibrations. So you end up with a very accurate description of your material, even when you have very subtle changes like the angle of rotation. So that's what's happening here. So just to let you know, we have this soliton network I mentioned before. So the grain boundary correspond to specific vibrations, which are soliton vibration. As you probably remember, soliton vibration are kind of delocalized vibration that can be either the total soliton network is moving as a whole, or in phase or out of phase. So I think it's time for me to get to the conclusion of my talk. And the question is that how are we doing in terms of the revolutions? So I think that we are doing pretty well. Lots of progress has been made. Students now study quantum mechanics, and their understanding of quantum mechanics increase their understanding of fundamental physics. There is, of course, always a saying that nobody really understands quantum mechanics, but I think this becomes a philosophical statement that we don't necessarily need to get into. We have to be humble as scientists, of course. We cannot say that we understand everything, because most people who say they understand everything are usually proven wrong very quickly afterwards. But we also have to have confidence in our understanding of what we know. and what we measure and how things can actually work together. So the experimental developments, especially in nanoscience, in material science, making structure with improved properties has been very important, along with theoretical developments, because this multidisciplinary approach between theory and experiment has been extremely beneficial for both. The theoretical development have benefited also from computational developments, because we can solve bigger and bigger problems with more and more accuracy. And of course, there is also the data handling that we are talking about. So all those approaches are multidisciplinary. It's actually very, very rewarding to work in these fields, because you can work with different people from different areas. And then there's been a century of new intuition about quantum monsters, as I said, and the behavior. So we start to actually get a good handle on the emotion of the quantum monsters. And so that means that we can also start to look into applications and, in fact, new development of what's happening in terms of the revolution and quantum materials, and therefore the second quantum revolution, which it's all about quantum information and quantum computing. So my last slide will be about acknowledgement. I'd like to acknowledge all the people I've been working with, and I hope I didn't miss too many people in this slide. And I'd like to thank you for your attention. And I'm sorry again for this power outage that just struck for a few minutes here with a thunderstorm. Thank you very much.
Thank you very much, Vincent, for your great talk. There was no questions during the talks, but now we are open for questions. So whoever wants to ask for a question, if you wanted to ask in Portuguese, I can translate. And if you want to ask, you can also write it down in English. But while people start asking questions, I will ask one myself. So you've been talking about this second revolution, second quantum revolution. Yep. But I would like to get a better grasp at what are the frontiers, the next frontiers on this revolution. What do you think are keeping us, or at least what do you think is the next things that we have to work on so that we can make really good profit of the quantumness?
Oh yeah. So I think that's right now we are the technological developments are in quantum computing. Quantum computing is really about being able to store more and more data, to have more and more processors that can do quantum computing. So this is where we are standing. So now a number of companies have prototype computers, but we are still a far way off to have a personal quantum computer. The problem, I don't know if you've heard about this, but quantum power, if it works as predicted, when I say it's because of the technological difficulties, we'll be able to do computing at a level that all the encryption, all the classical encryption media that we use now will be obsolete. So basically, nothing will be safe anymore. So everything will have to be reinvented. So it's a little bit like like people who fight, who use bows and arrows against machine guns. The bows and arrows were great when there was no machine guns, but when there are machine guns, they are no longer great. And so that's probably where we are. So there is also, of course, the ethical aspect of it. As always, when there is a new technology, that we have to make sure that it's available to most, and it's also not just, and it's also useful it needs use for the right reason, not for the wrong reason. So that's, I would say, where we are. So that's a complex, it's a complex topic, because it's both from a scientific point of view, engineering point of view, but also philosophical and ethical point of view. This is where we have to worry about. We have to work on. Okay.
About the twist graphene you just showed. You discovered one thing I didn't understand. So you make the calculation for a full lattice, like a huge super lattice, and you calculate the phonons on this structure. That's
right. So we have about we calculate the phonon on about, I think it's like 20,000 atoms system, and it's the issue, as you know, because you, of course, you know everything about phonon yourself, is the fact that if you do not get a very good relaxed structure to start with, you're going to end up with complex value for phonons, because these are instabilities in your phonon band structure. And so the hard part is not just to calculate the phonon, is to have one that's sufficiently relaxed that you avoid those negative frequencies. And unfortunately, because in the soliton network I was explaining, each atom moves, actually. It's not just, you know, we used to have that picture of twisting is on first order, there is no reconstruction, but that's not true. There is a very strong stress field that actually makes every single atom move. There's a reason why you have aspect of AA stacking, AB stacking, and in between. Of course, the AA stacking is the least stable, therefore the structure tries to minimize it, but cannot. There is a frustration there, a structural frustration, and so that means that the relaxation is not simple, but it's what basically describes what's happening. It's you need that to understand what's happening. So that's the major difficulty.
Great. How do you calculate the interatomic forces? Are they just like based on DFT or based on?
No, we can. I mean, we cannot use DFT on such a large system. So we use molecular force field. But this is interesting. You're bringing this up because if you use a simple Lennard-Jones like 612 potential, it's not going to work so well. So what has been shown in the literature and what we've used is the description as the one that was proposed by Kolmogorov and Crespi. So I mean, it's been a while. It was developed initially for carbon nanotubes, for multi-wall carbon nanotubes, and it's actually based off density functional theory, and so it's actually much more accurate, and you get the right friction coefficient, that kind of things that can be measured experimentally, and therefore you can validate the model.
All right, perfect. David de Souza Miranda is asking if, I'm not sure if he is asking you if you produce it, but he's actually about chevron type nanoribbon, doped nanoribbons. Can people produce that?
Yes.
Like doped.
Absolutely. They have. I don't know if I have those slides here, but the dope. Yeah, they've been done. I probably don't have that here though. If I do, I'll be happy to show you an example. Yeah, I don't have an example here. But yes, they've been obtained. I'm just trying to see if I can find one or not. Maybe not. No, I don't have that here. They are doped. This is very interesting. The question about doping, as you know, the question about doping is always the same issue. Is that real doping? When we talk about, and this is maybe a good opportunity to talk about this. When we talk about doping, when we take a semiconductor class, we are talking about fairly very, very, very low density of dopant. We are just talking about, a few electrons for 10 to the power 20 atoms, something like that. I don't remember the exact number, but this is very low density. In those structures, like the nanoribbon, like the chevron, you can actually dope them by substitution, just the same way as the doping that we learn when we do semiconductor, by replacing, for example, a carbon atom by a nitrogen atom, just the same idea. Is that the problem is that the number of atoms per cell is not large. So each time you replace one, you do much more than you do doping. And I called it doping in the past as well. I try to avoid calling it doping now, but because the ratio between the number of nitrogen atom, let's say, and carbon is pretty large compared to what we accept as doping in semiconductor industry. Why is that important? Well, the doping that we usually discussed in semiconductor is essentially to provide charge carriers. So basically what we say, we are changing the number of carriers. Well, when you are doping, when you substitute, let's say 1% of the atom, which is huge, you're doing more than adding electrons. You're actually transforming all the bands and the dispersion. So you have a different quantum container, basically. That's still interesting, but you cannot apply directly the physics of semiconductor as you would from that we do in diodes, for example. Yeah.
Okay. Also, if you can see, Paulo Gitasso is asking you to talk a little bit about TEM and tears on these types of systems, because you mentioned something about using SEM and AFM.
Yeah. So STM and AFM. Okay. Here is the thing that's a very good question. Of course, people have used a lot of TEM and high resolution TEM for carbon nanotubes and for graphene, in fact, as well. But the reason why I didn't show any structure like this for the nanoribbon is because one of the thing you need to build those nanoribbons is a metallic substrate. And so when you have a metallic substrate, it's great for AFM or STM, in particular for STM, but for TEM is not so great anymore. So before you can actually measure it, you need to transfer it to a TEM grid or what have you. And of course, this also applies to TERS, right? TERS, you need to use an appropriate substrate as well. So this is purely about transfer of the material than fundamentally. So it turns out that here AFM, STM are ideal given the circumstances.
Okay. There's also another question. So yeah, Ramon Sampaio is asking, Professor, do you think that by the end of the second revolution, the quantum computing information will be able to use today's internet structure?
Yeah, that's a very good question. This is an interesting question. I think that the reality is that everything that we are doing right now, which is based on the digital world that we are talking about now, just the 0 and 1s, right? So how are we going to move to qubits? I mean, this is a very good point. Probably not. Probably a lot of it is going to have to be improved. For example, at home, I get, when the internet works, so in other words, when there is power, I have a fiber optic. It's a fiber optic, which is faster than what I had before. But somebody had to come and dig a hole around my house to bring it to my house. It did not exist. I could not use the old technology. So yeah, it's very likely that we will have to worry about all those things. But I think that when you see the development of wireless network, wireless even power and stuff like that, I expect that things are going to evolve. Even if we don't go into quantum realm, we might actually still already be in a completely different context in terms of how we actually provide information. There will be fewer and fewer wire of any sort, actually, to be frank. So hopefully that will help if we do wireless to be a little bit more flexible in terms of moving into the quantum world. I mean, this is kind of science fiction a little bit at this point.
I have one last question. It's a more like a challenging question. So when the first computers were built maybe in the 60s or the 70s, but actually there's there's another question by Murilo. He's asking what are the open challenges for computationally inclined research?
The open challenges is that I think there are more opportunities than challenges. Of course, the challenge is let me just tell you let's take from the perspective of a student. What I realize now that students now who start studying in physics, for example, I mean it applies to other fields as well, but let's say physics just as an example. They usually start their studies with a pretty good understanding of computing. I mean, I am a computational physicist, and I didn't have even close to the understanding that they have in the first year when I finished my fourth year, because it's just coding is part of this. So this is an opportunity. Now the challenge is that those students who are very good at computing, they don't stay in physics because there are other sectors of the industry, of the economy that want to them and hire them. And of course, because of funding of science is so erratic, this is a big challenge we have for computational physics. But it's also true for experiment. There are usually people don't usually stay in research because it is not supported enough. Now, I'm sure the question was more about the challenges in terms of the opportunity about science. Really, what people do when they do research in computational physics and computational material physics is to always try to work at the cutting edge. So how much calculation can I do with the size of the computer I have? That's always, you have a computer and you will always find a way to fill it up. You will always go all the way to the edge. And so this is where people always work. So it's like when you buy an equipment, a microscope, you are not interested in using it in the normal circumstances. You want to push the limit. So this is what's happening. So it's a continuous challenge. And what has been interesting in the past 20 years or so is that the advancement in computing and the advancement in resolution, experimental resolution has pretty much met. So now we work on the same level in terms of accuracy and basically phenomena as experiment does. So we can, this handshaking is actually much stronger now than it has ever been. So I see more opportunities and challenges, frankly. I'm not sure I answered the question exactly the way it was posed, but I hope I did a bit.
Okay, so just to finalize with my question, so it took us about maybe 20 to 30 years for computers to go from the lab to the tabletop. How fast do you think that the second revolution will come into our houses instead of just into labs and great centers?
I mean, your guess is as good as mine. You know, what happens is that, as they say, right, making prediction is always hard, especially about the future, right? So, but I would say we are talking about. I mean, I know there've been times given in the media and so on, but I would think about at least 15 to 20 years. I'm not necessarily talking about personal computers, but something that can be kind of used more, you know, can be sold, can be bought, you know, instead of research. I think we're talking about at least, I would say, I would be surprised if we had anything before 15 to 20 years, but I would be happy to be wrong and if it happens before.
Yeah, okay, so now I will thank you again for this wonderful talk. It's been a pleasure, and congratulations on the lecture, and thank you very much. And hopefully next time you'll give this talk, next time you give a talk to us, it's going to be in person.
Yeah, thank you very much for inviting me, and it was a great pleasure, and thank you for all the great questions. And yeah, it's different to give a talk from home, but you know, the slides are the same, and the story the story is also similar. So it's good. Thank you very much, and enjoy your afternoon. See you soon. Bye bye.
All right, thank you.